So here, with the help of some stock footage from the company, I'm going to introduce the detection device that we're going to use for biogas leak detection this summer.
The new remote methane leak detector does not have to be within the gas plume because it uses laser technology known as tunable diode laser absorption spectroscopy. When the laser passes through the gas plume, the methane absorbs a portion of the light, which the RMLD then detects. Here's how it works. An invisible IR laser beam is transmitted from the launch port. To detect leaks, some of the laser light is reflected by the background surface back to the detector. This reflected light is collected and converted to an electrical signal that carries the information needed to deduce the methane concentration. With a normal background such as brick, concrete, or grass, the laser has a maximum distance of up to 100 feet away, and the laser light beam width is about 22 inches at 100 feet. It's important to note the laser light is selective to methane only, so it will not register a false alarm on other hydrocarbons or water. This signal is processed so that methane concentrations can be reported in parts per million meter, or ppm-m. ppm-m is the methane concentration times the width of the plume, while ppm measures absolute concentration. For example, the leak is creating a gas cloud of 1,000 ppm and is about 1/2 meter in width. The RMLD will read 500 ppm-m, while a FI would read 1,000 ppm. The RMLD uses a system of tones to indicate detections, concentration level, or fault conditions. The higher the pitch of the tone, the higher the concentration level. No sound at all will indicate a low light level condition or instrument fault. While using the digital methane detector, or DMD, no sound will be heard until a detection of methane occurs. The pitch of the sound will be relative to the methane concentration. The higher the pitch, the stronger the methane concentration is. In order for the RMLD to detect gas, 3 conditions must be present: a gas plume of sufficient size and concentration, a sufficient reflective background, and the laser must pass through the gas plume.
So here I am passing the device over our front yard surfaces, attempting to detect a source of methane. I have a sample of methane in a small Pyrex container that I captured from our cook stove, and as I sweep the device over the glass container, I obtain a positive methane signal and a concentration of somewhere around 10,000 parts per million meter.
In the event a leak is detected, the technician then needs to verify it. Larger leaks are easily verified by sweeping the laser in and out of the plume. In the event of a very low-flowing or venting leak, verification takes a bit more investigation. The RMLD can be easily used to determine if the leak is located on the meter or underground.
So here we are again with the sample of methane in a closed container on the lawn, and some of the challenges we'll face in using this instrument are, one, the kind of steady hand survey techniques that are necessary in order to get a reliable path integrated concentration measure, and two, the need in our project to estimate the flux of gas, the mass of gas leaking from a system, which will require some sort of reconstruction of the plume, so taking concentration readings at multiple points, multiple cross-sections in order to make that calculation. Not straightforward how exactly we'll go about doing that. So a number of challenges that remain for the adaptation of this device for our use, but we can also be thinking about the other sources of methane that we would like to quantify in the field setting in China, where we'll be this summer.